So I'm going to talk about climate change and sea level. And this is a presentation, interestingly, that I gave to HSBC, the bank, their senior team, because they're very interested in understanding more about climate change. So I thought it would be good for you to see the type of thing that senior executives in that bank are getting information on. So you can see the level of knowledge that they have, and hopefully there'll be some interesting things there for you as well. Oh, so there we are. That's me. I'm Martin, and that's me. I'm a glaciologist. I study the polar ice sheets in Antarctica and Greenland, and I'm standing on the edge of the West Antarctic ice sheets here, taken a few years ago. And beneath me is ice. This is a glaciated valley, and it's filled with ice, and the ice is about 500 meters thick there. And it's interesting, the ice. I mean, that's what I do. It's not what my research is all about, is understanding that ice. The great thing about Antarctica and Antarctic ice is it contains a record of the past. And it's kind of easy to understand how that might be. The snow on the surface is quite light, and it's light because it contains a lot of air. But that snow gets buried by subsequent snowfall, and it goes downwards into the ice sheets. So the further down from the surface you go, the older the snow gets. After about 70 years of being buried, the air in that snow gets cut off from the atmosphere above. And now you've got a time capsule. Now what you have with that air in that snow is a capsule of air from an ancient time that is now encased in the ice sheet. And as further burial happens, that snow turns to ice, and the air forms a little bubble within the ice. And again, it stays encapsulated. So what you can do in Antarctica is you can recover that ice from beneath the surface using coring. And this is a map showing all the very deep cores that have been taken from Antarctica, again, a few years old now. And we've learned so much about our past climate from these ice cores. This is the Vostok Ice Core. I'm going to tell you about Vostok Station, which is this thing over here. It's in the middle of East Antarctica. It's quite likely the most remote, inhospitable station in the world. Right? It's high elevation. It's freezing cold. The coldest temperatures ever recorded were recorded at Vostok Station, minus 89 degrees centigrade a few years back. But it is the location of this amazing ice core. This is the ice core facility. It's essentially a time machine. You know, it's like going back in time and taking a sample of the atmosphere from whenever that ice was once snow and taking the air bubbles out of it in that way. It's an amazing facility. But what they can do is recover ice down to the bottom. The ice thickness in Vostok Station is 3,741 meters thick. And they're drilled all the way to the base. This is what the ice core looks like when you take it out, all fine. And it's got these little air bubbles within it. And you can sample that air, put it through the right equipment, and you can detect and measure the atmospheric composition of gases within that air and relate it back to the past. So, of course, it takes a lot of, I mean, this sounds it's quite easy. It's very difficult doing this sort of stuff. And it's amazing that we've perfected how to do it. And as I said, there are quite a few ice cores now, but they've revealed amazing things about our past climate. And this is the graph we need to spend a bit of time on. So on the y-axis over here, we have carbon dioxide in parts per million. And on the axis over here, we have time, 400,000 years ago on the left-hand side to where we are now. Okay, you can see there is a periodicity, a rapidity to this signal. It goes from 280 parts per million down to about 180 parts per million. And it does that in repeated cycles, 280, 180, 280, 180. These are the ice age cycles. When the Earth's atmospheric composition is 280 parts per million of carbon dioxide, we are simply between ice ages as we are today. When it gets to 180 parts per million, we're in an ice age. And that means massive ice sheet over North America, big ice sheet over the United Kingdom and Scandinavia and Alaska and many other parts of the world, the Alps, the Himalaya, other places as well. And all it takes is that 100 parts per million, between 280 and 180. That's sufficient to cause the Earth's temperature to either fall or rise by about 4 to 5 degrees centigrade. And that's all you need to grow the big ice sheets. So carbon dioxide, but changing by just 100 parts per million, causes so much difference to our planet that we have to take a look at it. And that's why we're very keen to think about greenhouse gases in the atmosphere, carbon dioxide in particular. Now, this was taken a few years ago, current level of carbon dioxide being at 400 parts per million. But I have to tell you, it's more like that now, just short of 420 parts per million. So this is a real problem for us because the carbon dioxide level has never been this high for the last 500,000 years. In fact, you've got to go back a long way in the past to a time when it's been as high as this, which I'll come back to in a second.
May I interrupt and ask a quick question?
Yes.
So what exactly is creating this fluctuation of 100 drop back and forth?
Oh, yeah. Okay. So the carbon dioxide is doing the damage, right? It's carbon dioxide that's causing the big climate changes, but it's not being paced by carbon dioxide. The pacing comes by the way the Earth orbits around the sun. And so there are times where the Earth is in the northern hemisphere is pointing towards the sun, and there are times where it's pointing away from the sun. There's times where it's closer to the sun. There's times when the spin axis is more vertical or less vertical. All these parameters of the Earth's orbit are well known. They are very capable of calculating them precisely. We can do that in the past and we can do that in the future as well. And it's the orbital variations that are pacing these changes. So we know that for certain, but the orbital variations themselves are not enough to cause the climate change. They cause they like nudge the climate change. The amount of solar radiation difference between the maximum effect and the minimum effect of these orbital variations is a few percent. It's really tiny, and it's simply not enough in physics terms to cause the ice age cycles. It can pace them, but that's the worrying thing, because with these ice age, the orbital variations, you get a nudging to the system. The Earth starts to cool just a little bit as a consequence of the Earth's orbit. And that kicks in a load of other feedback processes, including carbon dioxide. In fact, the big relationship is between the atmosphere and the ocean, being forced a little bit by orbital variations. The Earth's oceans start to cool a little bit. They draw down carbon dioxide because cooler oceans are more productive biologically. And then with a cooler atmosphere, with less carbon dioxide in the atmosphere, you get further cooling, and so on and so on. So that's actually a real concern for us, because a little nudging effect that we get from orbital variations causes these other feedbacks to form or take away big ice sheets on our planet. But it's carbon dioxide that's doing the big damage. But thank you, good question. So the last 1,000 years, we can just take a sort of record of what the Earth's surface temperature is going to be like in the last 1,000 years. And there's quite a bit of scatter, but let's just put it all together for good reasons. We want to understand why that is. Essentially, the Earth's climate, with some variation, has been getting cooler for the last 1,000 years until you get to about the 19th century. And then we have this very large increase in temperature to about 1 degree centigrade from what it was, a little bit more than that actually, from what it was in 1850. Okay, so people have sort of said, this is the hockey stick. This is the so-called hockey stick of climate change. And we can put carbon dioxide over the temperature record, and then this is obvious relationship. But this is a graph I like. It's taken a few years ago again now, but it really sort of seals the debate about what this is all about. The variation in surface temperature on the planet, as we know, natural variation. This is getting slightly cooler till 1850, and then you get this big sharp increase. Atmospheric carbon dioxide concentrations, again, a bit of natural variability in here till you get to the 1800s, and then you go up. What's the reason for that? Carbon emissions, our own carbon emissions, either through land use change, cutting down forests, degrading wetlands and peatlands, over farming, those sort of things, and importantly, of course, the burning of fossil fuels. There are two ways to look at this. One is that it's a complete coincidence that temperature and atmospheric carbon dioxide and our emissions are all pointed in the same way. And the other interpretation, which of course is scientifically valid, is that they're related to each other. The Mauna Loa Observatory in Hawaii gives us a fantastic record of very recent carbon dioxide changes, and it's worth spending a bit of time on this as well. So this is the atmospheric carbon dioxide concentration, parts per million, what it was in 1960. A few things to notice about this. First thing is that there is this annual variation in the atmospheric composition, and that's simply due to the northern hemisphere summertime, where on the land lots of plants are growing and they draw down the carbon dioxide, And so you get a reduction in carbon dioxide. But during the winter time, actually, that doesn't happen anymore. And we see the effect of emissions. The difference between the Earth's ability to absorb carbon dioxide and the emissions of carbon dioxide gives you a net change. And since 1960 and before that, the net change has always been positive. And so every single year, we've been increasing a little bit of carbon dioxide into the atmosphere. But the problem with carbon dioxide is that, unlike some other very potent greenhouse gases, carbon dioxide isn't the most potent greenhouse gas, but it has a special quality, and that is it sticks around in the atmosphere. So it accumulates much more readily than, say, methane or other greenhouse gases would do. And so you get this constant accumulation of carbon dioxide over many, many years, and it goes up. The rate of change is also going up. So look at the gradient of the graph at this part in the 1960s, compare it to what it is now. We can stick the carbon dioxide value as it is at the moment up here too. And so this is the real problem that we have. We've got an increase in the rate of carbon dioxide emissions, even though we had COVID restrictions and not so much flying, and there was a reduction in the amount of emissions, we were still emitting. We were still emitting at a level of about 2016, 17, something like that. So the carbon dioxide values have gone up again this year, in spite of all the COVID restrictions, because emissions themselves will do the damage. The other thing to notice is that I was born in 1967, there we go, over here, when the atmospheric composition was 320 parts per million, and we're at roughly 420 parts per million now. So essentially what we've done is we've put in 100 parts per million of carbon dioxide in the atmosphere during my lifetime. Now, if I go back a few graphs previously to this one here, you can see another, very similarly, we went from 180 to 280 between 20,000 years ago, the last ice age, and 10,000 years ago. Well, we've done it, the same thing, in 50 years, not 10,000 years. It's like 200 times quicker than the natural world is capable of. So it's the rate of change that we're really worried about, in addition to the actual numbers here. In fact, it doesn't have any precedent. The last time we had 400 parts per million carbon dioxide in the atmosphere, you've got to go back quite a long way. There is no ice on the planet that is as old as we need. So we have to use the rock record to determine what the carbon dioxide concentrations were like. But you have to go back about 5 million years into the Pliocene. Pliocene is a very interesting time. The shape of the land masses was slightly different then compared to what they are now, but not hugely. But the atmospheric temperature was somewhere between 3 to maybe 4.5 degrees warmer then than it is today. Unfortunately, the sea level was about 20, maybe 25 meters higher then as it is today. So the Greenland ice sheet wouldn't have formed. The West Antarctic ice sheet probably wouldn't have formed too much as well. Maybe chunks of East Antarctica as well. So a real concern. If we keep emitting carbon dioxide, if we simply extend this line and extrapolate it, including with the rate of change, so unabated emissions of greenhouse gases, economic growth, coupled tightly with greenhouse gas emissions and fossil fuel burning, as it has been for the last 100 or so years, we simply continue that relationship. By the end of 2100, there'll be 1,000 parts per million of carbon dioxide in the atmosphere. Now, we have had 1,000 parts per million of CO2 in the atmosphere, because you've got to go back a very long way. 55 million years ago, the Paleocene Eocene thermal maximum is called. And then the shape of the planet, the planet was very different. The shape of the land masses were different to what they are now. This is deep geological time. There was no ice on the planet then. So sea levels would have been something like 60 meters higher then than it is today. Antarctica today, this is what it looks like on the left-hand side. This is what Antarctica would have looked like in 55 million years ago without any ice. It would have been a landmass with valleys and rivers and lakes and all those sort of things, and vegetation. So let's talk about sea level. So I'm a glaciologist and passionate about understanding the changes that are going on in the polar regions. They're fascinating. It's interesting, but it's also very serious, and we need to understand more. The polar regions, especially the Arctic, warming 2, maybe 3 times as much as the rest of the planet due to feedback processes and amplification processes that are going on there. So we're very concerned about it. But let's do a little thought experiment, and I want you all each to think about this. I'm going to ask some questions. Don't necessarily have to shout them out, but just keep them in your mind, and I'll give you the answers shortly. So, how much ice is on the planet today? If we melted all the ice on the planet, all the glaciers, all the ice sheets, and all that water either starts floating in the ocean because it displaces weight in water due to Archimedes' principle, or it just melts and the sea level goes up from the land into the ocean, how much would the sea level rise? So have a little idea in your mind about what that might be. Okay, you've got a figure. The answer is about 66 meters. So that's the potential sea level rise that exists on our planet. That's the ice that's locked on land at the moment that could be released into the ocean if it melted. Okay. Now, we have Greenland ice sheet and we have the Antarctic ice sheet, and then there are 300,000 other glaciers all around the world. If those glaciers melted, but Greenland and Antarctica didn't melt, how much would the sea level go up as a consequence, do you think? So we're excluding Greenland and Antarctica, but we're including every single other piece of ice on the planet. The answer to that is about 35 centimeters. By far, the largest store of ice on the planet is held in the polar ice sheets of Greenland and Antarctica. And that is why we're worried about them. I mean, the other ice sheets and ice caps and glaciers are very worthy of investigation. They are a fine barometer of changes. They have very important local effects as well, as you know yourself in India, of course. And then we can get a lot of information glaciologically by studying them. But it's the polar ice sheets. If we're worried about sea level rise, it's the real polar ice sheets that are important to us. Now you might ask, well, we live our lives on this planet, right? And we're sort of wired, our psychology is wired to thinking things have always been the way that they are, even though we know logically that can't be true. So we regard the planet that we inherited, that we were born into, as always being that way, but it really isn't the case. And you don't have to go far back in time. The last ice age is not really geological times, just 20,000 years ago. It's not very far back at all. But the Earth was so different then as a consequence of the carbon dioxide. But how much was the sea level lower 20,000 years ago compared to today? So we have big ice sheets forming over North America, over Scandinavia, Himalaya, the Alps, South Island, New Zealand, the Patagonia, many other places. Sea level was lower, clearly. And then it must have risen. So what we're talking about when we refer to sea level lowering at the last glacial maximum, we also refer to sea level rise between 20,000 years ago and 10,000 years ago. Well, you've got a figure in your mind. The answer is 130 meters. So when you look out to sea and you're looking at on your favorite beach, think about this, your favorite beach that you love and you go to repeatedly, look out to sea, and what you're looking at is, of course, the ocean. But actually, to a glaciologist, what you're looking at the surface and 130 meters beneath the surface, all of that water is melted ice from the last ice age. It's extraordinary. I mean, the geography of the planet, physical geography of the planet, was completely different then as a consequence of the big buildup and then melting of the polar ice sheets, paced by orbital variation, but driven by carbon dioxide changes. And it's an existential threat. This is something that London needs to take very seriously, and I know other places around the world as well. But if all the ice is gone on our planet, London is in peril. And you might say, well, that's unlikely to happen, but there are two things to mention. Firstly, that we know when the carbon dioxide goes up, the ice sheets melt, and the last glacial maximum is a good indicator of that, 130 meters. We know when the carbon dioxide level gets to 400 parts per million, you get somewhere around 20 odd meters of sea level rise. And so London is in peril. It's an existential threat to this city and to many other cities around the world. And the evidence in the records is obvious. And we know it. We've measured the sea level going up. This is a record of global sea level for many tide gauges all around the world from the 19th century to the present day. And again, you can see a couple of things here. 20 centimeters of sea level has happened. Half of that is due to the thermal expansion of the ocean. So the oceans get warmer and the water expands. So half of the sea level is through that. The other half is through melting of glaciers and things, and very small amount from the polar ice sheets. So, but there are a number of things to mention. Firstly, the rate of change, again, is going up. So 0.8 millimeters per year in the 19th century, 2 millimeters per year in the middle of the 20th century, and now 3.2 millimeters per year in the 21st century, and going up still. The deglaciation record between 20 and 10,000 years ago was about 13 millimeters per year. So we are now well within an order of magnitude of that other sort of second phase of global deglaciation, not caused and forced by paced by orbital variations, but paced by us. Now, it's fair to say that thermal expansion has been really important, and melting of glaciers has been really important, and the contribution of Antarctica and Greenland hasn't been so important to those 20 centimeters. But as I said, the potential for Greenland and Antarctica to start being mobilized by global warming and causing sea level is phenomenal, and it's starting to happen. So this is the IPCC's report, the fifth assessment report, looking at emission scenarios and what the contribution of Antarctica and Greenland is going to be like under various emission scenarios. You know, you have the very low emissions, the medium one, and the high emission scenario. So that's essentially what the IPCC is trying to do. We did it a few years ago, and since then we've been able to put observations down, some satellite records of what the ice sheets are doing, and plot those records over what the projections actually were. And the worrying thing is that the observations are tracking much more closely with the worst case scenario than they are with any of the other two. So Antarctica is starting to be mobilized by global warming, and you can see it in the data. This is a satellite compilation of changes in Antarctica. It's from the cryosat, so it's a radar altimeter, could be a laser altimeter as well. The IceSat is another satellite that does the same job. Essentially what it does is the satellite gets a very accurate measurement of the surface elevation of the ice sheet, and then goes back another year later at the same point and takes another measurement. And you look at the difference, and you can see whether the ice sheet surface is going up or down. The only explanation, there's a couple of explanations. One could be a dynamic ice process change, and you can certainly see that happening in these regions here. This part is thickening and this part is thinning because this is an area that's slowing down and that's an area that's speeding up. That's all fine. But in many other parts of the West Antarctic ice sheet and in the East Antarctica as well, it's because the ice surface is, the ice sheet is being melted. And we're really concerned about that. Very concerned about West Antarctica and this part of East Antarctica for this reason. If we strip away all the ice, we take the ice off and look underneath the ice, this is what the bed of the Antarctic ice sheet looks like. So keep your eyes, if you will, on this region over here as I take the next slide. Do that first, okay? This region over here. This is what the Antarctic ice sheet looks like when you take away all the ice. The blues are where the bed is below sea level, and it's very below sea level, 2.5 kilometers below the level of the sea in this region here. And this is why I'm really worried about it. Antarctica isn't melting because the atmosphere is getting warmer. It's melting because there is ocean heat that is being delivered from the deep ocean toward the ice margin, and that is doing the damage. In fact, ocean forcing of ice sheet melting is like 10 times greater than what atmospheric forcing can do. So it's the marine parts of this ice sheet that we're really worried about. And the danger is twofold, because as you can see, this part of the ice sheet here, the margin, if you go further inland, the bed gets deeper. It's called a retrograde slope. And there are a number of processes that act to accelerate the rate of ice loss under a retrograde slope. It's called the marine ice sheet instability hypothesis. That is, as the grounding line gets melted and moves further inland, it gets deeper. And so the ocean's ability to melt that ice gets enhanced. And that's why we're really, really concerned about the West Antarctic ice sheet acting through marine ice sheet instability. But it's not the only process that we're worried about as well, because of the fringe of the ice sheets in Antarctica, go back a couple of steps, are these areas here, very flat over here, this area over here, this over here. These are the ice shelves, the very thick floating slabs of ice. 300 to 1,000 meters thick, these floating ice shelves, and they act as an important back force to keep the grounded ice where it is on land. And if they're not there, then the ice can flow more quickly into the ocean. But importantly, if they're suddenly taken away, what you can get is a vertical wall of ice. Now, ice is a very interesting mechanical substance. That is, it flows when you apply large pressures over long periods of time. That's what we understand now, glaciers flow. But you experience brittle failure if you apply stresses over very short periods in time. And the mechanical property of the ice is such that it's unable to support itself if the vertical ice wall is about 100 meters high. Unfortunately, with the great thicknesses, the huge thicknesses of ice that we have in Antarctica, if the ice shelves are suddenly taken away, then that is exactly what we'll see. We'll see vertical walls of much more than 100 meters in the West Antarctic ice sheet, and the ice is unable to support itself. Now, you don't have to melt the ice, it simply collapses under its own weight and falls into the ocean. Once it's fallen into the ocean, it's displaced its weight in water under Archimedes' principle, and the sea level change happens. So we're particularly worried about this. It's called the marine ice cliff instability. So these two processes, marine ice sheet instability, marine ice cliff instability, are hypotheses at the moment. Right? We've never really seen it. We've seen a bit of it actually in Jakobshavn in Greenland, but Glacier in Greenland, but not so much in Antarctica. But the worrying thing is that if they are applicable in Antarctica, we're likely to see accelerated ice loss and much more sea level coming from Antarctica and Greenland than we're experiencing at the moment. I should also say, look also at this part of Antarctica. This is the Tottenham Glacier. East Antarctica is always thought about as this sort of sleeping giant and nothing really much happens. West Antarctica is subject to a lot of change, but not in East Antarctica. But it's not necessarily true. Look at this region here, and I'll take you back to the bed. Well, this is what the bed looks like in Tottenham Glacier. And again, you can see it's full of blues. And if you go further inland, you can see it gets deep blue as well. So it's not quite as marine, obviously marine-based as the West Antarctic ice sheet, but it is still marine-based. And again, this is a real concern to us. The bits of the ice sheet that are changing right now are the bits of the ice sheet that we're most concerned about. We did a paper shortly, and I asked Somali to let you have a copy of this. Otherwise, I think it's under a paywall, but you can have a copy from me personally, and that's okay. I and a few other authors, we looked at 21st century sea level rise under the Ipcc, and we concluded that there was a bit of, we think there's sort of underestimating what the worst case scenario could be for global sea level rise in this century. The Ipcc sort of restricts their thinking to a sort of likely scenario of an upper limit of about 1 meter, maybe 1.1 meter. But when you look at what that actually means, a likely scenario, it's somewhere between 66 and 100% certainty. So that means it could be a 1 in 3 chance of it being outside that range. It's unlikely under a worst case scenario to be lower than what, a meter or so, but it could be higher. And that's what we say in this paper. And we sort of point out a number of reasons for why that might be the case. We need to take sea level seriously now. This is not something we're parking into the future in decades' time. It's happening now. And within the lifetime of say, our children, it might well be that if we don't do anything about carbon dioxide emissions, if we let it rip on our planet, it might well be that our children will see sea levels of several tens of meters, maybe a meter or more, and with serious implications for how we live on this planet. Now, when I talk to HSBC and other organizations, I don't stop at sea level, of course. I want people to understand the enormity of the problems that we're facing. And we can talk about it in 4 ways. We did this work for the UK government a few years ago, who wanted to understand what damage climate change would give and what we could avoid if we invested in climate solutions now and drew down carbon dioxide. We did it in 4 stages, 3 stages: the no mitigation, the Paris Accord, keeping our pledges, the INDCs, now NDCs, of course, and capping emissions so that we hit the 2-degree target. And by the way, the 2-degree target, as you know, is only 1 degree warmer than it is today. So when we talk about 2 degrees, we mean just a further 1 degree of warming. When we talk about 1.5 degrees, it's only another ½ a degree of warming, because we're nearly there right now. Heat waves, of course, are significant, and we're experiencing them, and in India definitely is the case. We looked at the exposure to heat waves, and some of this is repeat exposure, but we calculated through our partners in the Meteorological Office, University of Reading and other places, that if we don't do anything about carbon dioxide emissions, there could be 12 billion cases a year of exposure to extreme heat. And if we do reduce emissions, we can take that down, but it'll be higher than it is today. And this is higher than it is right now. So that's the most important thing to notice. There are problems that are locked into this. There is further warming that is coming, and we can't do really anything about that. The damage has already been done. We have done the damage. But there are so many things that we can avoid if we reduce emissions actively. And heat waves is one of them. Unfortunately, not such a good story for cropland decline, because we are over or misusing the land surface on our planet, and we are seeing soils being eroded, and our ability to grow crops is going to decline as a consequence of that, and other problems as well. And a real problem if we don't do anything about emissions, but we'll still have a problem even if we cap emissions for those reasons. Coupled to that is our ability to get fresh water, either for agriculture or for drinking. And again, this speaks to the overuse of groundwater resources, aquifers, that sometimes take centuries, sometimes thousands of years to build up, and we're depleting them in decades, much more quickly than they're being filled up. And so that is presenting a real problem in many parts of the world. The other is flooding. And again, this is quite a good story as well, because for every 1 degree of warming that a parcel of air experiences, it can contain 7% more moisture, more water within it. And so under a scenario where the atmosphere is several degrees warmer than it is today, the atmosphere will simply be capable of containing much more water within it. And so it's obvious that the opportunity for flooding is going to happen as a result of that. You don't need me to tell you this, of course, because in India you live in a monsoon country and you experience this effect yourself. But if it happens in many other parts of the world through atmospheric warming, you can see the damage that it might be. And this is a photograph in 2017 from Houston. This is Storm Harvey, and I was actually in Houston around this time, and it was phenomenal. I mean, firstly, it was a tragedy, of course, but secondly, it was predicted. And that's an amazing thing about this, that our understanding of the physics of the atmosphere and the way that the weather works, and indeed the way that the climate works, is very good these days. And this storm was predicted days in advance of when it actually happened. So much so that I actually evacuated out of Houston and went to Austin several days beforehand, and very well that I did that, because it would have been stuck there. So, relying on the science, just like we were speaking before this seminar started, is really important. Investing in science, getting really good information about the way that the atmosphere works, the way that climate works, can help us in situations like this, provide the early warning systems that we need to alleviate the worst of the damages. Very similar story, of course, to the pandemic and COVID-19, and investing in science in that way too. So here we are, we're at this point in time, 2021, we're over here. At the moment, we're tracking the worst case scenario. That is undeniable. All the efforts that we've made on reducing emissions, on getting governments to agree to changes, on the rollout of renewable energies and electric vehicles and all of those things haven't made much difference, unfortunately. Good progress, but not enough. So we're tracking worst case scenario. The INDCs from Paris, they take us to 3 degrees. We need to pull it down, carbon dioxide, to net zero by the middle of the century. This whole analysis took us to 2 degrees centigrade. Actually, we need to pull this curve down even further if we're going to hit 1.5 degrees. Now, how do we do it? Again, we did this analysis, looked at 2 scenarios: taking action today, 2020, well, last year, or leaving it a decade. And if we take action today, the cost of the investments that are needed is going to be about 1.7% of gross domestic product. If we leave it a decade, then it goes up, the cost goes up. And so waiting 10 years makes it more expensive. The other thing to notice is that if we decarbonize now, we can do it at somewhere between 2 and 9% a year, the decarbonization rate. And we know we can do that. Sweden achieved 4% decarbonization year on year for a decade in the 70s and early 80s to decarbonize their economy quite well. So we know it's possible that we can do it. But if we leave it 10 years, then it's going to be somewhere between 7 and 14% a year. We just haven't achieved that. Then we're in new territory if we think about that. The rollout of gas and carbon capture and storage and nuclear and wind and all those things are so much greater if we leave it 10 years compared to what we do now. Remember that the rollout of coal that fueled the Industrial Revolution year on year was about 50 gigawatts per year, and that's the sort of growth rate of it. We would have to invest in these technologies at a far greater rate than we invested in coal during the Industrial Revolution and afterwards as well. So again, it's unknown territory. The short answer is we need to take action now. It is possible that we can achieve what we need to if we take action now. It will cost less, right? And we know we can do it. We have the technologies available to do it. If we leave it 10 years, it will be disastrous. In fact, the best time to have done this was about 20 years ago, when we really understood this problem, understanding that the problem is happening, understanding that we are the cause of it, and understanding that we can do something about it. And for 20 years, unfortunately, we've all been sitting on our hands and not making the differences and the changes that are necessary. So that's my talk, and I wanted to give you a similar talk to what I gave to HSBC, so you can see what's on the minds of sort of global executives in this space. So when you talk to them next, you can kind of get an idea about where their thinking is, I hope. But I want to leave you with this lovely picture of Antarctica, and this is in West Antarctica, and the mountains poking through the surface of the ice in this wonderful, amazing place that I'm so lucky to do my research in. And it's a place that I hope we can preserve in this amazing, pristine state that it is today.